Hi everyone, this is Dr. Swaminathan Yasam. Now we will discuss about the topic called state space representation of the continuous time system and state equations. So first thing, what do you mean by continuous time system and discrete time system? Continuous time system means the time based on the time instance, we cannot predict the output. The output may be frequency, amplitude, phase, etc. Discrete time means the output is predicted either 0 or 1. That is discrete. That is digital means digit plus AL. So digit means you can say either 0 or 1. So you can predict. So here we will see a continuous time system. So first thing, introduction. This is the introduction and the state space representation in the CT system and needs state space model following the activity, state diagram, state equations and state transition matrix summary. So first thing, in the state space representation, the mathematical model of the physical system, it's called input, output, and state variable in the first order differential equations. And the state of the system can be represented in the state vector within that space. And again, the CT system signals as inputs and outputs are called continuous time signals. And what are the needs means system description without examining its specific physical meaning, and next to understand or to manipulate the property of the system. In the classical control theory, the system model is represented by a transfer function. Analysis of the control tool is based on the classical methods such as root locus and Bode plot. It's restricted to the single input, single output system, and it depends on the information of inputs and outputs, and it does not use any knowledge of the interior structure of the plant. And again, it allows only limited control of the closed loop behavior of the feedback system is used. So here these are all the concept. U1 of t to ur of t is the input vector u, and the output vector y means y1 of t to ym of t, and the system is described by the state variables called x1 to xn. And the state model, the system output is defined by any system variable of interest. That is, in terms of a set of state variable does not necessarily include all the variables, that is directly engineering interest. And also the linear state equation, that means a system variable may be represented in a linear combinations of the state variable xi and the system inputs ui. And consider this equation x1 dash to a11 x1 plus a12 up to b1, that is same thing up to xn. So you can differentiate d divided by dt in terms of x1 to xn. So x1 dash means dx1 by dt, and you can make equal to a11 to a1n and n minus 1 into amn. So you can get x1 x2, that is another thing and the same thing for b. So you can make x dash equal to ax plus bu. So this is the state model, and this is another equation same like y is equal to cx plus du. And following with the activity you can make so the simple example I would show. Third point, the pi rates and the Caribbean. So pi rates of the Caribbean. So this is a simple thing. So you make the connections. So these are all the answers of the activity. And these are the state diagram. You can make u of t is the input, b is the block, and summer, and make this x dash of t. You can make this x dash of t is the input to the integrator, then you can get x of t and given to the c and the summer and the y of t, and again x of t is feedback through the a block to the summer, and again the u of t is given the feedback to the another sum model. And the state equations you can make v of t and rc. So using this state variable, so you can say state variable means voltage and current. So you can make this Kirchhoff's voltage law and Kirchhoff's current law for any equations. So for state equations, so v1 is equal to x1, v2 is equal to x2, then you can get the voltage divider law, v1 minus v2 divided by r plus c into dv1 dt equal to 0. So you can substitute the same thing for another second loop. V2 minus V1 is a common thing because the input output voltage V2 V1 and plus V2 by R, that is a second voltage, and the C into dV2 by dt equal to V of t divided by R. So again, and another thing, second circuits you can make x1 x2 1 by RC 1 by RC 1 by RC minus 2 by RC, because the 2 is combinations, and x1 x2 plus 0 1 by rc into u. So this output equation y is equal to 1 0 and x1 x2. So based on the state equations, you can get the state transition matrix x dash of t equal to a x of t. That is a homogeneous means same equation. Then Si of A, Si minus A x of S equal to x of 0. The inverse Laplace transform again you make, and the partial differential equation, then you can get this inverse Laplace transform. And again based on this, you can get the state transition matrix x of t is equal to pi of t into x of 0. Pi of t is a normal matrix, n into n matrix in the unique solutions, and pi of t you can get a into pi of t. So pi of 0 is equal to I. So these are all the properties of state transition matrix. Pi of 0 is equal to e power a0 equal to I. Pi of t is equal to e power at. Then you can make this inverse. And again pi of t1 plus t2, you can make this e power a into t1 plus t2. So you can differentiate e a t1 into e a t2. So based on this, you can get the third point. And the fourth point, pi t whole power n means pi nt. So n is given to the a, that is n is given to the t side, and same thing for the phi. So t2 minus t1 and t1 minus t0. So you can write the t2 minus t0 means t1 minus t0 and pi t2 minus t1. So these are all the summary of this today's session. So state transition matrix, and state equations we discussed so far. Thank you.